Hi everyone. Today we're starting our last unit that we're going to be able to fit in this year, which is finding the derivatives of special functions. So this is going to be really important for first year university, no matter which calculus you're taking, whether it's for life sciences or for engineering or for business or for mathematics. So we're starting off. This lesson is called Introducing E, and our learning goal is to find the derivative, meaning the slope of the tangent, to functions of the form y equals e to the exponent g at x. These are exponential functions, but instead of the base being 2 or 3 or 4, it's the number e, which we're going to find out about or learn about in this lesson. So we know pi is a special number. The number e is also special, and we're going to see why it's special. It's really special because of calculus, and you'll see why. It is named after Swiss mathematician Leonhard Euler. Pi and e are both irrational numbers, so meaning decimals that go on and on forever, never repeat, never stop. So if you find on your calculator, there's going to be an e to the x button somewhere. It could be a shift key, like a shifted key, or it could be another one. I'm going to find the one here. Mine is shift, and it looks like ln, which we're going to learn about in the next video. So mine's shift, and then it gives me that e. And then e to the 1, for instance, is approximately, remember, because this is a decimal that goes on forever, but the calculator will tell you 2.719281828. Okay, so it's approximately that, whereas pi, is approximately 3.14157. E is approximately 2.71828. Okay, but it goes on and on forever. Why is e such a special number? So consider the function f at x equals some base b, so that's a number, could be any number, to the power of x. According to the definition of the derivative, so we're going right back to first principles, the first principles formula for finding the derivative of a function. The first principles formula is that f prime at x is equal to the limit as h approaches 0 of f at x plus h minus f at x over h. So if we want to determine f prime at x for the function f at x equals b to the x, that's what we're going to think about right now, then it's the limit as h approaches 0. So think about first f at x plus h. If f at x is b to the x, then f at x plus h is going to be b to the power of x plus h. Okay? So I can replace f at x plus h with b to the power of x plus h. Minus f at x is defined to be b to the x all over h. Okay, so we can't let h approach 0 because then the denominator would approach 0. So there's got to be something we can do to get around this. So one thing I'm going to look at here is if we look at this as one chunk and this is our other chunk, they actually have a common factor. We can common factor out b to the power of x using our exponent rules. Okay, so if our greatest common factor is b to the x, then I would use my exponent rule, and I have to divide this first chunk, this first blue chunk, which is b to the x plus h, by our greatest common factor. So b to the x plus h divided by b to the x. So according to our exponent laws, when we divide powers with the same base, we keep the base b and subtract the exponent. So x plus h minus x, which gives us the x minus x gives us 0, b to the h. Okay, so when we divide the first b to the x plus h by b to the x, we get b to the h minus b to the x divided by itself is 1 over h. So another rule we learned about when we were working with limits in the first chapter on calculus was that if we had something like b to the x that doesn't depend on h at all, we could leap it in front of the limit there, because b to the x is not going to change depending on what h does. So we can rewrite this as b to the x times the limit as h approaches 0 of b to the h minus 1 over h. Okay? Now this limit that's left here turns out to be something very important. Okay, so we're gonna just focus on what does this limit mean. So our question, what is this limit? Okay, so if we remember, so we have our formula for f prime at x, this is our first principles formula. For f prime at x, which is the derivative at any specific point. But we also had a first principles formula to find the slope of the tangent at a specific point. So if you remember, that formula was f prime at a, where a was the x value of that specific point that we wanted the slope of the tangent at. And it was the limit as h approaches 0 of f at a plus h minus f at a over h. And that's where we're going to figure out what this limit that I've put in a square box of blue actually represents in this case. Okay, so if I want to find f prime at 0 instead of a, that would give me the limit as h approaches 0 of f at 0 plus h is just h minus f at 0 over h. Okay? Now remember, this is based on the function so I'm going to go back here. It's based on this function here, f at x equals b to the power of x. So if I go back up here, f at h based on this function is going to be b to the power of h. Okay, so I can replace f at h with b to the power of h. And what's f at 0 according to this function, or b to the x? So f at 0 is b to the power of 0. And we know from exponent rules that any number to the power of 0 is equal to 1. So f at 0 is 1. So back down here, minus 1 over h. So look at what f prime at 0 is, and look at the limit that was in this box, and they are exactly the same. Sorry, I went out of frame a bit there. So in other words, f prime at x is going to be the base b, some number b to the x, times f prime at 0. Okay, so what was in the blue box represents f prime at 0 if f at x is equal to b to the power of x. Okay, so f prime at x, the derivative is b to the x, which is the function, times the slope of the tangent to that function when x equals 0 is basically what that's saying. Okay, so again, this is still a proof. We're going to get to a very interesting result soon. So as the base b changes, so does the value of f prime at 0. For a very fortunate base, it's going to turn out that f prime at 0 is actually going to equal 1. And it would follow that f prime at x would be b to the x times 1, if f prime at 0 equals 1, which is b to the x for that special base. So for some very special base, the derivative of b to the x is b to the x for that very special base b, that very special number, which you probably may have guessed is going to turn out to be e, but we're going to prove that to you going forward. Okay? So we're going to do that kind of using the technique that you may have learned in advanced functions. Okay, so we're going to investigate this base. We're going to evaluate f prime at 0 according to the formula we came up with, being the limit as h approaches 0 of b to the h minus 1 over h for different values of b. Okay, so here's our base. We're going to let h, this is what you did in advanced functions, instead of having it equal 0, which we can't, we let it be a number like 0.0001. Okay, so if I'm putting this into my calculator, so I'm letting h approach 0, but really I want h to approximate this number 0.0001. So if I put 1 in first, and I'm following this, so 1 is my base, I'm going 1 to the exponent 0.0001, 1 to the anything is 1, so I should already know that, but I get 1. Subtract 1 is 0, divided by 0.0001 is 0. Now we're trying a base of 2. So the calculation I'm doing in my calculator, again, this is a part of a proof, but it's interesting. So 2 to the power of 0.0001 equals, subtract 1 equals, divided by 0.0001 equals, and my calculator gave approximately 0.693. Remember, we're looking for where is that going to, what number does that base have to be for f prime at 0 to equal 1? That's what we're looking for. Okay, so we've gone from 0 to 0.693, so we're getting closer to 1. Okay. All right, so now we want to change the base to 2.5. So I'm doing 2.5 to the exponent 0.0001 equals minus 1 equals divided by 0.0001. And I get, I'm getting closer to 1 again, 0.9163 approximately. Okay? So now I'm going to let my base be 2.6. So 2.6 to the exponent 0.0001 minus 1 divided by 0.0001, and that gives me 0.9556, 0.9556, getting closer to 1. So now we're going to try 2.7 to the exponent 0.0001 minus 1 divided by 0.0001. And that gives me 0.993. Getting closer to 1. 99 now. So now let's try 2.71. 2.71 to the exponent 0.0001 equals minus 1 equals divided by 0.0001. We get 0.997. Closer to 1. 2.718 we're going to try next. 2.718 to the exponent 0.0001 equals minus 1 equals divided by 0.0001. 0.99995, so 0.99995, getting really close to 1. Let's try 2.8. 2.8 to the exponent 0.0001 equals minus 1 equals divided by 0.0001. We get 1.02. So now we've gone 296 or 297. So we've gotten greater than 1. So it's in between 2.718 and 2.8 is going to be that number where the limit as h approaches 0 of b to the h minus 1 over h is going to equal exactly 1. Okay? And it turns out that that special base is e. Okay, that irrational number e, which is approximately 2.718281828. It doesn't repeat, it never ends, that special base is e. So what does that mean then? So why is e such a special number? It's because when f at x is e to the x, then f prime at x is e to the x times 1, which is just e to the x. So the derivative of f at x, the derivative of e to the x is e to the x. Okay, so that does not happen. That's very special. The derivative is itself. Okay? If we apply the chain rule, so we have f at x equals e to some function of x, not just e to the x, but e to some function of x, then f prime at x is going to be, so we use the chain rule, the outer derivative is e to the g at x, so this is our outer derivative. And then the inner derivative, so we're going to multiply that by g prime at x, which is the derivative of the exponent. The inner derivative is going to be the derivative of the exponent. Okay, so for instance, that means if f at x, you can see up here you can, was e to the x squared, for instance, then f prime at x, the outer derivative, we just leave e to the g at x, so it would be e to the x squared times the inner derivative, so that's going to be the derivative of the exponent. So the derivative of x squared is 2x. Okay, so that's how the chain rule works there. In other words, we would have f prime at x is, and then we'd probably write that as 2x e to the x squared. Okay? All right, so that's our chain rule. And that's kind of all the proof part now. Now we're just going to practice using that idea, using the chain rule here. So we're going to determine the derivative, and we're going to write it as simplified as we can. Okay? So determine the derivative. If f at x is e to the 2x, what's f prime at x? So following the chain rule, f prime at x is going to be, so we repeat e to the 2x, and then we multiply by the derivative of the exponent. So the exponent is 2x. Its derivative is 2. So f prime at x we would write as, if we multiply those together, we would get 2 times e to the 2x. Okay, remember e is a number, and where is x? It happens to be in the exponent. This is an exponential function. And that reminds me, I should go back to, you're probably wondering why I had this graph here. Okay, so look at this graph. This is the graph, actually, of the exponential function y equals e to the x. Okay, and remember f prime at 0 means the slope of the tangent at 0. So if we were to find the slope of the tangent where x is 0 and draw a tangent in there, and I apologize guys, I didn't bring a ruler, so I'm going to rough it here, but if we were going to take the slope of the tangent to y equals e to the x at 0, the slope of the tangent would be 1 there when x was 0. Okay, that's what we proved with our chart there, that f prime at 0 was 1 for the function y equals e to the x. And it looks like 1, like if I drew this with a ruler, over 1 up 1 over 1 up 1 should be the slope of the tangent there. And that's what it is. Okay, and then this is our exponential function y equals e to the x. If you remember from advanced functions, exponential functions have this curve. There's a horizontal asymptote along x equals 0 that you never cross or touch but get closer and closer to. Okay, and then grow exponentially. So that's what the graph was for. All right, so back to finding the derivative. So here's our next exponential function, y equals e to the exponent x squared minus 3x. So y prime, or you could use dy by dx, whatever you prefer, is going to be, so chain rule says we repeat e to the x squared minus 3x and then multiply by the derivative of the exponent. So here's my exponent. The derivative of that exponent is 2x minus 3. And there's not really an easier way to write that. I mean, the back of the textbook might write it with the 2x minus 3 in brackets first, or second, depending on the textbook. But either way, that's simplified. All right, so C. So now we have x squared, which is one function of x, multiplied by e to the x, which is a different function of x. So two functions of x multiplying together, which is going to involve the product rule. So for the product rule, we're going to make this chart here. So the first function is x squared, and the second function is e to the x. The derivative of x squared is 2x, and the derivative of e to the x is e to the x. So then we can use the product rule to find y prime. So derivative of the first times the second is 2x e to the x, plus the first times the derivative of the second, x squared e to the x. So there's the calculus, there's the derivative, but we can look at this and see if we can put it into simplified factored form. So there's my two chunks. What's in common with them? 2 no, x, yes, and e to the x. So if we divide each chunk by x e to the x, we would get 2 plus x. So there it is in simplified factored form. So we have x times e to the x times 2 plus x. Okay, so the next one, h at x equals e to the 3x over x squared. So now we have a quotient rule, a function of x, an exponential function, divided by just a quadratic function of x, I guess. But we would use the quotient rule, so first, second function derivative. So our first function is e to the 3x, and our second function is x squared. So the derivative of e to the 3x according to the chain rule is e to the 3x, and then times the derivative of 3x, the exponent, which is 3, which I would write as 3e to the 3x. And the derivative of x squared is 2x. So we're using the quotient rule. Make sure you can see I'm in the frame here. So quotient rule says derivative of the first times the second. So I'm going to write that as 3. I'm going to put the x squared before, since everything's multiplying together, before the exponential. And then minus, so I'm multiplying these two together. I'm going to put the 2x before the exponential, all over the second x squared squared. So now I want to put it in simplified factored form, so I'm going to look in the numerator at my two chunks and see what's in common. So 3 and 2, no, x squared and x, yes, x is in common, so it can be part of the greatest common factor, and e to the 3x is in both chunks as well. Okay, so I'm going to divide the first chunk, 3x squared e to the 3x, by x e to the 3x is just going to give me 3x, minus 2x divided by x is 2, and the e to the 3x's divide out, over x to the 4th. Okay, and the last thing, if I have x on top and x to the 4th on the bottom, that's like having an x to the negative 3 in the numerator, or an x to the positive 3, which is what we would prefer in the denominator. So there is h prime at x in simplified factored form. Okay, and then if we look at e, we have a function of x, square root of x, multiplying by another function of x, so we have to use the product rule. So we're going to go first, second, function, derivative. So our first function, I'm going to write root x as x to the exponent 1/2. And our second is e to the x. And the derivative of x to the 1/2 is 1/2 x to the negative half, using the power rule. And the derivative of e to the x is itself. So I'm going to back up here and use the product rule this time. So derivative of the first times the second is going to give me 1/2 x to the negative half e to the x plus x to the half e to the x. So there's the derivative. Now I want to write it in simplified factored form. So this is a good one. So anytime you have a coefficient that's a fraction, you want to make that part of the greatest common factor. So I've got my half compared to my 1 here, which isn't really showing, okay? And I'm going to take the half. And then x to the negative half, because it's the smaller exponent. And then they both have e to the x. So that's my greatest common factor. So I'm going to use some scrap paper here to go through what the dividing looks like here, so everyone's on the same page. So if I have a half, x to the negative half, e to the x, divided by a half, x to the negative half, e to the x, they're exactly the same, so I get 1. And then plus, so then I'm dividing the second blue scoop, which is 1 x to the half e to the x by a half x to the negative half e to the x. Okay, so I'm looking at this one here. So 1 divided by a half. So let's think about that. 1 divided by a half. How many times does a half go into 1? If you know it's 2, great. If not, you can use the rule multiply by the reciprocal. So 1 divided by half is 2. We've spent a lot of time on x to the half divided by x to the negative 1/2. So that's going to be x to the half minus negative a half, which is x to the half plus half, or just x to the 1. And e to the x divided by itself is 1. So when you divide those, you're going to get 2x. So convince yourself that that's true. And then we can put that here. So there we've got it in factored form. It's not quite simplified yet. And that's because we want to write it with a numerator and a denominator, no negative exponents if we can help it. If there isn't a negative exponent in the question, the rule of thumb is you don't want to have one in your answer. So that means in the numerator, I'm going to keep my e to the x and my 1 plus 2x. And in the denominator is going to be the 2. And the x to the negative 1/2 can come down and become x to the positive 1/2 or square root of x. So that's how we would write that in simplified factored form. Okay, on to F. Y equals 1 plus 5e to the negative 10x all to the 4th. So we've got this all to the 4th power function kind of look to it. So it's chain rule first. So y prime is going to be 4 times the whatever to the 3rd, and then we got to multiply by the derivative of what's inside. So the derivative of 1 is 0. The derivative of 5e to the negative 10x is going to be 5e to the negative 10x, then multiplied by the derivative of the exponent, which is negative 10. Okay, so then just kind of to simplify things here, we've got this 4, 1 plus 5e to the negative 10x all cubed. The 5 times the negative 10 is going to make negative 50e to the negative 10x. But this is a monomial term. So we can multiply a monomial by a monomial. So that's going to be 4 times negative 50 is negative 200 e to the negative 10x times 1 plus 5e to the negative 10x cubed. And there it is in simplified factored form. And we kind of use that rule of thumb again. If there's a negative exponent in the question, there can be a negative exponent in the answer. Okay, in G, so G we've got a function of x, 3x squared, multiplying another function of x, e to the 2x. So we've got to use the product rule here. So the first function is 3x squared, and the second one is e to the 2x. The derivative of 3x squared is 6x, and the derivative of e to the 2x is e to the 2x times 2, because the derivative of 2x is 2, or 2e to the 2x. So y prime is going to be derivative of the first times the second, 6 x e to the 2x plus the first times the derivative of the second. So 3x squared times 2e to the 2x is going to be 6 x squared e to the 2x. And then when we want to look at our two chunks here and figure out the greatest common factor. So 6x e to the 2x, divide each of those chunks and we get 1 plus x. And there it is in simplified factored form. All right, so now we're going to apply it in a few different ways. Our first one is usually our easiest application. So determine the slope of the tangent to that curve y equals 3e to the x squared at the point where x is -1. So first we want to find y prime. So if y equals 3e to the x squared, y prime is going to be 3e to the x squared times the derivative of x squared, which is 2x. Or we could write that as 6x e to the x squared. But we want it at -1. So y prime at -1 is going to be 6 times -1 e to the -1 squared. So that's going to give me -6 e to the 1, so -6e. And just like when you're working with radians and pi, you leave things in terms of pi. Same with e, we want to leave things in terms of e. So you're going to say, therefore, the slope of the tangent is -6e. Okay? And if you wanted to know what that was on your calculator, you could do e to the 1 times -6. And, oops, I got a syntax error there. E to the 1 times -6. So it's about -16.3 approximately, but you would want to keep it in terms of e. Okay, now we have an implicit differentiation question here. Find dy by dx given your original function is implicitly defined as x e to the y plus 6x squared y. So we've got two product rules within this. So we have a function of x multiplying by a function of y, and another function of x multiplying by another function of y. So for my first product rule, go off to the side here. So first, second function derivative. So my first is x, and my second is e to the y. Derivative of x is 1. So according to the chain rule, the derivative of e to the y would be e to the y times the derivative of y with respect to x. Okay, and then our second product rule is going to involve 6x squared y. So our first is 6x squared, our second is y. The derivative of 6x squared with respect to x is 12x, and the derivative of y with respect to x is dy by dx. All right, so then deriving now. So starting off with this one, derivative of the first times the second is e to the y, plus the first times the derivative of the second is going to give me x e to the y times dy by dx. And then going on to our second product rule, plus 12xy plus 6x squared dy by dx equals 0. So I'm going to keep my terms with dy by dx on the left. And subtract e to the y on both sides, and subtract 12xy on both sides. Now I want to get dy by dx by itself, so I'm going to common factor dy by dx out of the left side, and that'll give me x e to the y plus 6x squared divide both sides by x e to the y plus 6x squared. And therefore dy by dx is equal to negative e to the y minus 12xy over x e to the y plus 6x squared. Okay, and remember with implicit differentiation, we're usually not really concerned about simplifying it, just being able to get an expression for the slope of the tangent or find the slope of the tangent at a point. In this case, we just needed an expression for it. Okay, and our last question. The number n of bacteria in a culture at time t in hours is given by the function n at t equals 2,000 times 30 plus t e to the negative t over 20. So part A says find the number of bacteria in the culture at t equals 10 hours. So that wants us to find n at 10. So it's going to be 2,000 times 30 plus 10 e to the negative 10 over 20. So n at 10 is going to equal. Okay, so how do I put this in my calculator? So you want to find, I usually start with the e key in this, so I'm going to do, find my e to the x key, e to the exponent, and then bracket, negative 10 divided by 20, closing bracket. Okay? Oh, I got a syntax error. I haven't used this calculator for that before. E negative 10 divided by 20. I'm not sure. I got 0.60653. I'm not sure if that's right. I'm just going to run and get my other calculator because I haven't used that one before. Sorry guys. So I've got E on this one to the negative 10 divided by 20. Yeah, that's right. Okay, so I don't need to use an exponent button on this calculator, but this one automatically puts it down for me. So for your e to the negative 10 over 20 part, you should get 0.60653, etc., etc. So that's just this part right here. So now you've got to multiply that by 10, so times 10. So now I've got 6.0653, etc. Then I'm going to add 30 and press equals 36.0653 and then times 2,000. And that gives me approximately, so this is a number of bacteria, 72,130.6 bacteria. You could round up to 31 if you wanted. Doesn't matter. Okay, so at what rate is the culture growing at t equals 10 hours? So as soon as you see rate, you know that you have to either find an average rate if it says average, but if it just says rate, then you're thinking instantaneous rate, which is the slope of the tangent. So I have to find n prime at t. So we're going to start off with n at t, how it was originally given to us. And we're just going to make it look a little bit more easier to find the derivative of. So I'm going to expand. So n at t, so I'm still just rewriting n at t. So 2,000 times 30. So I'm distributing the 2,000 is 60,000. And the reason I'm doing that is because I know the derivative of a constant is just going to be 0. So that 60,000 is going to be easy to derive. Plus 2,000 t e to the negative t over 20. So now I can find n prime at t. So the derivative of 60,000 is 0, which I don't even have to write. But here I've got a product rule. I've got 2000t, so a function of t multiplying by another function of t, e to the negative t over 20. So I'm going to have to use the product rule. So my first function is 2000t, and my second function is e to the negative t over 20. So the derivative of 2000t is just 2000. The derivative of e to the negative t over 20, so I repeat, e to the negative t over 20, but then I need to find the derivative of negative t over 20. So if you remember back to when we first started deriving stuff, so if we had negative t over 20, we'd probably first write it as negative 1/20th t, so that you could see that its derivative is just 1 times negative 1/20th t to the 0, or negative 1/20th. So the derivative of this exponent is negative 1 over 20. So you could probably write that as negative 1/20th e to the negative t over 20. And then these correspond and these correspond. So n prime at t, we know the derivative of the 60,000 was 0, so derivative of the first times the second, so 2,000 e to the negative t over 20. And then I'm multiplying this by this. If I multiply 2,000 times negative 1 over 20, I get negative 100. Then I've still got my multiplying by t, and then I'm still multiplying by e to the negative t over 20. Okay, so at this point I could substitute in 10 right now, or I can put it in simplified factored form if I want to before substituting the 10 in. As long as you're good with your calculator, it doesn't matter. I'm going to simplify it just for practice anyways. So in common with 2,000 and 100 is 100. There isn't a t in both, but there's an e to the negative t over 20 in both. So 2,000 divided by 100 is 20. And then minus 100t divided by 100 is t, and e to the negative t over 20 divided by itself is 1. And now from here I'm going to find n prime at 10, because I want to find the rate, the instantaneous rate at 10 hours. So that's going to be 100 e to the negative 10 over 20, or negative 1/2 if you've spotted that as well, that's fine. It's good actually. Times 20 minus 10. You might want to simplify as much as you can before putting it in your calculator. So 20 minus 10 is 10. 10 times 100 is 1,000. E to the negative 1/2. And then put that into your calculator. So e to the exponent, and then you can put in negative 0.5, or you can put bracket negative 1 divided by 2. E to the negative 1/2, you should have 0.606536, and then times 1,000. So n prime at 10 is approximately 606.5, and then it would be bacteria per hour. So at what rate is the culture growing at t equals 10 hours? 606.5 bacteria per hour. So therefore, the culture is growing at 606.5 bacteria per hour. All right. Thanks, guys.